We also have different sales and support people resident in different locations to support our customers. Now, MELS, we are a people-centric organization. We are not an organization that has large production shop floor and things. We are more of a knowledge organization. We have people who do a lot of design, who work on implementation, support to our organizing customers. We operate in 5 business verticals. And when I say 5 business verticals, the first one being what we call as the global sourcing group, where we represent companies from across the globe in India for electronic assembly, test and repair products. So being right from capital equipment for being soldering systems, for testing, test and measuring equipment. A good example I can say today, you're talking about EVs, there's a lot of testing that goes on into them. Or even the satellites, and we work a lot with the Space Research Organization. So we do a lot of representational business as sales and support organization here. And in the last couple of years, we've been doing a lot of work on the semiconductor space as well. We represent international brands who have products that help in terms of the semiconductor manufacturing, both in fabs as well as in OSATs. The second business group is our electronic systems, where we design and develop our own ATEs, automated test equipment, and we do a lot of work with the defense and public sector units, DPSUs we call it. We have 2 other groups that focus on the industrial automation, where we set up assembly lines for our customers with a lot of robotics, electromechanical systems. We use a lot of PLCs, and the other business group that we do is on the digital technology solutions. Again, we are factory oriented. We do a lot of software work, but these are all on the factory shop floor. That is maybe acquiring real-time data from shop machines, being able to take decisions on how the manufacturing floor must go. And today we use a lot of artificial intelligence on that as well. And of course, the last one is our simulators business group, where we do operations and maintenance training simulation. This is on either the railways, the air force, or we do it for the metros as well. So that's a brief about what MELS does. Now, let's talk about ESDM and semiconductor. So the first thing is, I did understand that most of you here are about the third year in terms of your course progress, and a mix of different streams of engineering that you are here. It's important that we understand that ESDM or semiconductor is not only for people in electronics, okay? There's the whole ecosystem there, and we need people from all streams to be involved. This morning I was discussing with one of the other speakers that when we have today the technology, even material science and chemistry becomes extremely important when we talk about engineering as a whole. Okay, there's a lot that matters in terms of contributing to such topics. I'm going to limit my presentation to a more industry level and a macro topic. I'm not getting into any technical subjects on how something works or how it is done. We'll focus more on the macro overview. To start with, so what is ESDM and why semiconductor matters, right? So the first point, we'll have to understand what are we talking about when we say ESDM. Okay, that's a terminology of electronics market, and then there is a terminology we say ESDM. Okay, electronics system design and manufacturing. So this covers everything from right your electronic circuits, okay, right from your PCBs, or you start going into circuit level below that, and includes everything like the manufacturing and up to the product manufacturing on your smartphones or your electric vehicles or your automobile or medical devices. And there's a subset of that, okay, while today there's a lot more hype on the semiconductors. The semiconductor part is, I would say, is a subset of your ESDM, and these are basically the brains of your modern electronics. So in fact, the upcoming slide talks about how the evolution has been when we talk about semiconductors, and you can treat them as the new oil for the digital world. So when we talk about ESDM, it includes all aspects of an electronic system, right from your product design. It could be the chip design. We talk about embedded system and manufacturing of the up to the finished goods. Okay, so again, ESDM can be applied to different sectors. So it's not always a specific sector we talk about. Within that, you may do products and solutions for telecom. It could be for automotive. It could be for medical devices. There are a lot of defense and aerospace applications as well. So as again, we talk about verticals in the industry and then the solutioning that goes into the different verticals. Now, today it's very difficult to imagine anything without electronics. So I think be it your mobile phones, I think that's one of the most common use cases that has become with pretty much everyone being your wearable devices or today automotive. So what used to be purely a mechanical equipment or a device now has enormous electronics in it. I think the number of boards and chips on a new car these days or even on a two-wheeler, I think there are phenomenal number of amount of electronics. In fact, if the electronics doesn't work, the mechanical system doesn't work. So that's the amount of electronic involvement in all the products that we use. So and software can only run on this electronics. So there's a lot of push on the software and the IT field earlier. Now, Srinivasan also mentioned that there's a lot of push on the electronics sector because software can only run on this electronics. Today, I think the most valued company you have, NVIDIA. You see they've moved from where they were long ago, looked at as a company who does video graphic cards. I think they started off there and it looked like, okay, there's a company making graphic cards. And today, pretty much any AI system cannot run without an NVIDIA based system, right? They are the leaders in the market. So electronics is extremely important, and then more so now is becoming the involvement of semiconductors. And when we talk about semiconductor, India is in a very nascent stage. Okay, we should say we were a little behind. Okay, I do not want to sound very negative about it. We've taken a little more time than the rest of the world to catch up on that, but I think it's always late than never. And so as part of the Atmanirbharta and all the other ecosystem push, I think a lot of investments are being talked about in the semiconductor space. And I should say that this is one of the most complex technologies. Of course, medical is a great area to be in. I think you talk about in microscopic terms. And in semiconductors, you start talking about in nanometers. And globally, this is about a $600 billion industry and is expected to go up to about $1 trillion by 2030. So there are a few facts that you'll have to understand also when we talk about ESDM as a market in India. Now, ESDM in data of about 2023, it was about 2.09 lakh crores. That is roughly about, let us say, a $25 billion market. And in 2028, we are looking at about 9.09 lakh crore, which is a CAGR. It's a growth rate of about 34% year on year. So in 5 years, pretty much the whole thing is going up about 4 to 5 times, okay, multiplying. So you can imagine the amount of opportunities this brings in, both from a financial perspective, from an employability perspective, from the amount of technology that it will drive. And so India, we are targeting at about $300 billion worth of electronic production. That is again aligned with the $10 trillion economy that we are talking about as a country. And you can see that in the last few years, the mobile phone revolution and the manufacturing has driven quite a bit of this. Okay, and as a country, we are now moving slightly outside of that. You can see earlier only about 26% of the mobile phones that India used were manufactured in India. Today, 99.2% of all the mobile phones that we use are manufactured in India. And we, as a country, we have more than 1 billion mobile phones that are being utilized. And also as a job opportunity, you can see that we have about 1 million jobs that will be created next year only in semiconductor industry. So we talked about the investment of about 76,000 crores. So this is the investment to bring in investments, and so that's roughly about 10 lakh jobs that are going to get created within a year's time, and that's where the industry is starting. Over time, this will also become much more, and then it's expected to be a couple more million jobs over the next 5 years. And there are, of course, a lot of major players like Micron and Tata making investments in India at the moment. So what is fueling this growth? So why is there all these investments here, and why this interest in this? So one is the rapid electronic consumption growth, I would say. Okay, the first one is, you see this, I just explained, there's electronics pretty much everywhere. Be it even these lamps that are here, they have a lot of electronics in them today. Okay? They're all smart, and your TVs are smart TVs, the air conditioners are smart air conditioners. There's a lot of electronics that goes into all of them, and there are a lot of wearable technologies that's coming in too. So I think we are not able to think about any product or solution where we are not using any electronics or a chip. The next is the automotive boom. And when we talk about automotive boom, yes, we've always had, let's say, cars, trucks, buses, and so on. But how connected they are, and then we are talking about self-driven cars. So all these are again driving a lot of innovation, as well as a lot of involvement of these electronic components in them. 5G rollout and the digital infrastructure. We want to be more and more connected. We want to use faster internet, and this also leads to a lot of network equipment. So don't only look at the towers. Okay, the number of towers may not be so many, but there's a lot of back-end systems that go into enabling this kind of a network. And so there are a lot of routers, switches, and other network equipment, and there's a lot to do on the security space as well. So there are a lot of electronics going into that. And to enable all this is the capital equipment and being able to set up the factories that run these. So today, we have enormous number of factory automation that is being deployed. So again, we talked about a lot of robotics. We have assembly lines. We want smart manufacturing. We want to be able to understand what is being produced in which machine, and we want to have machine-to-machine communication. So with all this, there's a lot of electronics that gets driven there as well. So these are some of the major growth drivers, and sensor technology and embedded systems is also extremely crucial. So we do not want large machines now, we want edge computing. So there's a lot of embedded activity that happens onto these devices. And in fact, I was at a conference yesterday where we were talking a lot about sensor technologies and how that has to get. So today, India still depends a lot on importing sensors with all these investments and technology like MEMS and NEMS coming in. So I think we potentially should have a lot more sensor development in India as well. So what is the network and the support that we have? I think the government is doing a lot for this as well. We have something called the PLI, which is the Production Linked Incentive Scheme. So the government is trying to say, okay, so for all the manufacturing that we do, of course we have the Atmanirbhar Bharat, so the Make in India initiatives. So maybe initially it puts a lot more pressure on the industries because it's much easily available overseas, so organization can bring in products and service the customers. But it's been very good that the government took this initiative, and over a period of time people have started developing products here and started to implement them. So that's good. And then as the PLI scheme, so for every goods that is manufactured, the government is talking about a 4 to 6% incentive that they can provide. Specifically on the electronics, we have this China Plus One policy. So just around COVID or after that, the whole world realized that we can't be dependent only on China. There's one country that's manufacturing for the world. And so they started thinking that we must have one more country or more countries, right, that can service their requirements. So that's another thing that's helped in the overall move. The government is also doing a lot of budget allocation. If you can see, we had estimated last year was about 5,747 crores on this space. And now we are talking about this year about 8,850 crores. So there's a lot of focus that's being put in terms of the country's investment. And also a lot of states, including Tamil Nadu, there's a lot of state-driven initiatives on this. So they are setting up manufacturing clusters. Okay, I think now there's a lot of push around Thoothukudi. You can see a lot of investments being announced now. There's a new car company that's set up a factory, and then that whole ecosystem is being built. Karnataka has announced a lot for this ESDM. I think they are in fact talked about investment that will bring about 20 million jobs only on this electronics related sector. Then of course Gujarat is doing a lot of semiconductor companies are setting up their OSAT facilities in Gujarat. So there's a lot of initiatives that are being taken by the government as well. And of course there's something called as the ECMS, that's a scheme that the government has also announced, is the Electronics Component Manufacturing Scheme. So with all the production, I think over the last 10 years or 15 years, with the government's drive, there's been a lot of push in terms of localizing the electronics, but we are still far away from making components, and component manufacturing is becoming something that's important so that we become more and more self-reliant, and that's something that the next scheme that's coming up for that. Now there's a semiconductor fever, so I think that's something you all have to catch up on. Now, and I'll probably in my adjacent slide tell you why I'm talking about all this. Now if you look at semiconductors, we've had semiconductor lab, there's SCL in Chandigarh, that's been around for I don't know 30 plus 40 years, but we've as a country not focused a lot on the semiconductor market. That's something that's just starting up. There are at least about 12 to 15 companies who have now announced different type of projects that are setting up either OSATs or fabs. Fabs are lesser to the moment. And the government is again giving a lot of subsidy on this. A lot of the 75,000 crores that we talked about is part of the subsidy. So when organizations are willing to set up and invest, the government gives a lot of subsidy on the capital equipment, which is, most of these industries are highly capital intensive. There's a lot of plant and machinery that needs to be set up to be able to manufacture semiconductor. And with all this, we are still not in the semiconductor map yet. Okay? India is almost nowhere on the map. So we have primarily countries like Taiwan, USA, Korea, China and Japan are the major countries in the semiconductor space. But again, what this means is with all this push, there's a lot of opportunity, cutting edge technology for all of you. And that's an area, if you think that I'd like to be in cutting edge technology area, this is something that you can definitely focus on. Of course, we are a leader in the semiconductor design. More than 30% of all the semiconductor design happens here. So we've continued to be a services country, and so we do a lot of work on that. Now, I'm going to take about 3-4 slides to explain the semicon process. I'm not sure how many of you have gone through or understood the semicon manufacturing process, and I'm not sure if it's part of the course curriculum now, but I think it's going to be quite important because just this is going to give a huge job opportunity in different streams, right? And I'll list that as well. So it's one of the most complex technologies ever. So to manufacture a semiconductor product, there's about close to 950 processes. Okay, the 950 processes, I wouldn't say that, they are same process. There are many of them are iterative, right? Your fab, the wafer is a deposition process. You got it. Deposit, etch, clean, deposit, etch, clean. So it goes through multiple processes, repetitive process. And one wafer, just one silicon wafer, the entire start to end with all its in-between time that it has to be given for cooling takes close to about 3 months to make one wafer. So you can understand as a process, and what you're seeing is probably, let us say, one wafer can produce maybe enough chips to go into maybe, let's say, 500 phones, 200 to 500 phones. But you see the volume, so it's going to take 3 months to get it. So there's a lot of parallel process that goes on. And 18.5 million liters of water being used every day. And to understand the context, okay, so I talked about SCL in Chandigarh, which is the semiconductor laboratory. So India still, our technology is 184 nanometers. That's what SCL Chandigarh has. Okay, and nanometer is what, I think a billionth of a meter. 1 billionth of a meter is a nanometer. And TSMC, which is Taiwan's leading semiconductor manufacturing plant, is at 3 nanometers. Okay, so that's the scale that which we are looking at. And today, all your processors that run your laptops, your computers are all micro scale, and the smaller it gets, you're able to make more intelligent and wearable devices and so on. And a 3 nanometer fab costs close to about $20 billion to make. And I just talked about the whole India's ESDM market being 25 billion last year. Okay, so you can see the amount of investment that has to go into setting up a 3 nanometer fab. A quick history. So many years ago, so there were vacuum tubes, and then we started going to transistors, and then ICs, integrated circuits. So the movement has been progressive, but the growth in the technology has been rapid over the years. Okay, I always talk about this. You look at the curve of manufacturing or anything that happens in the world, the learning curve. What took 100 years some time ago, then started becoming about 15, 20 years, and then now we are talking about months and weeks before technology changes. You talk about AI, which is now becoming very popular. Maybe about 3-4 years ago it's when it started, but AI has been actually around for about 40 years, I think, if I'm not wrong. Okay, we had AI for so long, but it was very slow, and now the ecosystem and the available infrastructure is further fueling rapid growth in these. So in one silicon wafer, this is how it looks. And this NVIDIA Super AI graphic processor, it has about 50 billion transistors in them. Okay, so that's the size we are talking about. So 2 slides ago I showed you so what transistor looked like, and now you're talking about 50 billion transistors going into one of these. Okay, so that's how the miniaturization happens and what semicon is able to do for you. So in the semiconductor manufacturing process, you have right from the wafer, you've got to the ingots, you can slice it, and then you have an oxidation photolithography process, then you have etching, planting, and I talked about an iterative process. You have a lot of iteration happening around this area, okay, between your etching, your implantation and the metal deposition, and then you have all the other packages. So this is only getting the wafer itself, then they get diced into small parts, which then gets packaged into a form that you typically see as a chip. Okay, so but there's a lot that goes into before that's happening. And why I'm coming to this is each of these areas by itself present huge opportunities for people to work. Right? There's a lot of engineering that goes into each of these processes that will get you to look at the nanometer scale in terms of the operations that happen on them. So this is just explaining the different process. So the crystal growth, then you have the ingot slicing. So you have the ingots which are fractions of millimeters in which they've got to get sliced, and then they've got to get oxidized. So right from people who are looking at chemical engineering to people in the mechanical stream to mechatronics, they've got to have different type of work. So I would say that pretty much till it comes into the packaging level, people in the electronics field don't have much work. So it's till then you get there, unless at the design stage. Okay, so that's what we are really talking about. Just a visual idea of how a semiconductor fab looks like. A lot of machines, a lot of automation on them. Clean room environment. People are not allowed to just walk in there, and you normally don't get to go into an semiconductor fab as well. Very few people are normally allowed for the amount of cleanliness that has to be maintained in a fab. And again, an example, so you can see this machine here. This is actually what we call as a EUV machine, and is used for the photolithography, just one of the processes these machines can be. And again, there's a lot of work that goes into implementing such machines at high precision and at few high volumes. So some of the career opportunities that I would like to talk about. So career opportunities can be different, depends on whether you want to be on the design end, you want to be at the manufacturing end, you want to be at the post implementation, so or you want to be even in sales and marketing. So there's a lot of opportunities there. So either you can be part of the process, you can work on the optimization areas, and you can also look at reliability. So a lot of work that is required in the quality front as well. So what type of degrees and certifications help to work in this ESDM and semiconductor market? We look at people from different streams, right from electronics, ECE, computer science, mechanical, mechatronics. There's a lot of work that goes on. So I talked about oxidation, I talked about cleaning, dicing, and all these processes require a lot of chemistry and physics that go into that. So that's something that is key. You look at the skills, there are a lot of skills. So apart from the course or the qualification that you have, in parallel is very important that you gather a lot of additional skills. You understand circuit design, VLSI, CAD, and a lot of embedded programming. That's required part of this. And there are a lot of programs that are also done by IITs, NPTEL, and then we talk about there are executive programs also for people who have been in the industry, because it's a new area that's coming up, so people can go and reskill themselves. And there are a lot of short-term courses also offered by ESSCI, which is the Electronic Skills Council for India, who offer a lot of short-term courses. Some of them are diploma courses, some of them are certificate programs that they offer in VLSI, IoT, and embedded systems as well. We talked about semiconductor. There are a lot of materials and inputs again that goes into it. So again, each of this has a lot of engineering going into manufacturing these subparts. Okay, so there are more than a lot of cleaning process, but things like, let's say, the soldering related, the bonding, the lead frames, again have a lot of activity to go into each of these. And I would like to touch upon the last line item which I have written here as automation. So when any of these kind of factories are set up and we are looking at huge volumes to be produced, there's a lot of automation that needs to go into it. So it's not something that manually we can ever produce. So we need a lot of automation that involves all the material handling, controls, the management of this whole process, real-time monitoring of it, and intelligently being able to adapt to the changing requirements and maintain the amount of quality that goes with it. And there are a lot of key leading companies who are hiring, again for different type of skills. You have global giants like Micron, Qualcomm. All these we are talking about in India. Okay, so I have not even looked at the global scale. So opportunities here, of course, a lot of people would be interested in looking at the global market, but the action is now in India and it's going to be there for the next 15-20 years. So I think we look at opportunities here, and even the government and defense is doing a lot of work here, and there's a lot of opportunities there, be it ISRO, DRDL, or the semiconductor lab. So what could be the next steps? So when we say next steps, I would strongly urge all of you to look for very good internships in these areas. I think my last slide talks about opportunities that we have in our organization. So, but in internships, I think you all have to start doing a little more study. Today it's just not Google alone, so you've got a lot of other AI-based research tools that help you understand the subject pretty well. It can even give you a guided course curriculum in terms of guiding you on how to learning these subjects. And you must understand it and then start getting into some area where it's of your interest. Okay, go through some internships and participate in different college and tech clubs. I would say again, your own college and university might have different programs that they are conducting, but there are also a lot of national level programs and competitions. So it's not about winning the competition, that is not important. I think it's the participation, and in this process you learn a lot. So that's a lot of online certification programs. There are a lot of industry expos that I will also urge all of you to go and attend when you find time. So there are programs like the India Electronics Week. There's a semicon exhibition that's going to happen, I think next month in Delhi. Then there's one Productronica that's coming in Bangalore, and I think attending such events also will help you understand what's happening in the industry. What you might then suddenly find something of interest to you, and then you can pursue that as a career. And yeah, I think in interest of time, I'm going to skip a little, but what we are talking about in each of the process, we have different streams of engineers who can work. So do not assume that anything to do with ESDM and semicon is fixed only to people who are doing the electronics domain or in the mechanical. It could work for pretty much everyone. Has a role to play in that in improvements. And now there are, within semicon, we broadly classify into two parts. One is the fab, and then the other is the OSAT. And the fab is really people who make the wafers and then get it up to that form, and then you have the OSATs who package it into the chips and then give it in a form that is usable in your electronics. So there are a lot of companies who've announced projects, and so that gives you a lot of opportunities in the market. Some more companies who are announcing. Even again, Coimbatore has companies who are big in semicon. We are having in Zoho who is announcing something south of here. And of course, there are large Indian companies for fabs as well. So one important takeaway that I want to leave here is that it takes a long time to learn the technology that's in ESDM and semiconductor. There are people who spend their entire life only in this domain. Okay, and for people who are just getting in, yeah, I would say it could be a little daunting at the beginning, the amount of technology that is involved in it, but I think that perseverance is important, and you would always feel that, oh, this is a fantastic place to be in, giving the cutting edge technology that this offers, and it's going to be that way for maybe the whole length of your careers as well. So I would strongly urge that have the perseverance, and then do not quit very soon saying, okay, I went into this industry, it looks too complex, but it's a fantastic industry to be in. And that's my last slide, talking about some opportunities at MELS. So we continuously have interns every year, so we would be happy to have interns from your organization as well. Feel free to write to us. We have on our LinkedIn page, on our website, we have opportunities, and we have pretty much every semester we have 10 to 12 students that we gather for an organization of about 200 people. That's quite a number, but we work on different projects. We do on some product development, we work on some of the automation areas, we do some of the software and robotics as well. So please feel free to write to us. And we also have continuous recruitments we do year on year at the entry levels. So that's something that we would be happy to look for in your college as well. Thank you, and that's the end of my presentation, and if there's time, I'll be happy to take some.
Thank you, sir, for sharing light on how semicon framework coupled with advanced electronics is accelerating the shift towards smart technology. Can we have a Q&A session? The students can raise their questions.
Yeah, there is no intelligent question. Okay, every question is good question. So I think feel free to ask something, and if I know the answer, I will respond to it. So with the silence, I put it one off to either you understood nothing of what I said, or everything was very clear. And
Good morning.
Good morning.
So, what is scope of ESDM specifically in defense industry?
Sorry, can you repeat? ESD?
Scope
Defense.
of ESDM in defense.
Okay, so it's very interesting that you took up this point. I talked about a conference I was yesterday. So the last 2 days I've been at a strategic electronics summit in Bangalore that was extremely focused on defense and aerospace related technology. Now, defense is one area where there's a lot more complexity as well, given the importance of national security on it, with all the cyber security that goes on, and the rate, the first time right, I would say, right? So, for example, you have a, let's say this electronic device here. Okay, so what happens in this space? You're not going to lose lives, nothing's happening, right? If I click and it doesn't happen, I might try clicking it again. That's the amount of, it's always nice to have a product that's very reliable, but I would take this as a device which is much lower in its seriousness, okay? But in defense, that doesn't happen. So when you have warfare and you're looking at, let's say, launching a missile, when you click, it's got to work, and if it does not, you're losing thousands and millions of lives. Potentially, that could be the impact it has. So there's a lot of importance that's given to ESDM in the defense sector, and that is one reason why the country also, I talked about a lot of government organizations like DRDO labs, trying to indigenize a lot of the electronics and this whole ecosystem in India. They're trying to promote this whole thing being developed within the country, purely that we do not want to have reliance on other countries in this space. And I would also take an example. I don't know how many of you followed it, maybe about just before the Iran war started, or the Israel-Gaza war started in the first few months. You would have noticed that a lot of pagers that were used by Iran was remotely detonated by another country. Okay, so when this happened, you see, they relied on technology from another country in defense, and that's a critical factor. So ESDM plays an extremely important role, and I would say that the amount of accuracy and repeatability required there is far more than in the consumer electronics.
Thank you, sir.
Thank you.
Sir, I have a question.
Yes, sir.
Good morning, sir.
Yeah, good.
My question is, in the beginning, what kind of skill set or knowledge you gained in the industry?
Okay, what I would say is the current curriculum that you people are going through by itself is pretty good, and that should help you understand the subjects, right, into what you have to get into. But any axe requires sharpening, right? You will need to go through, that's where I recommended going through some type of certification programs, going through these finishing courses, I would say, which will help you understand and identify niche areas where you can work. Okay, so today I know that there's a lot being effort taken by the government in ensuring the curriculum matches what the industries are requiring, and of course that's what organizations like ICT Academy are also enabling. And you need to polish what you have learned so far and then try to adapt. And do not expect that day one I go in, I'm going to be able to do wonders in the market. That doesn't happen. Yeah, there are always prodigies. I don't want to look at the outliers, but pretty much your course curriculums are now being aligned with what the industries require, and some fine tuning is okay. I would strongly urge that you look at some of these online certification programs, and that by itself will be good enough for you to look at opportunities in this sector. Thank you.
See, this is related to, of course, curriculum only. So, All India Council for Technical Education says that since the application of AI is increasing in our day-to-day life, now the syllabus is being reoriented in terms of application of AI in civil engineering, application of AI in mechanical engineering, application of AI in electrical engineering. Like that, is there anything like application of AI in, I just want to have an exposure about that, so that the knowledge about these things may give a better exposure. I thought of asking this question.
Okay, you look at AI in multiple areas. Of course, the use of AI in these finished products, that's a whole domain to talk about. Okay, so I think the use cases are as good as our imagination is. But let me maybe talk about a little more on how AI helps in terms of design, research and development of this, right? If you look at that, again, what took us months of research to understand the topic, I should admit, for today's session, it took me about 10 minutes spending time on some AI tools like Perplexity or Gemini, which helps me. In fact, 2-3 slides of mine has images that are generated through AI as well. Now, that's what AI can enable you to do. And for any of you, if you would like to understand this, right, you can run through it with AI to understand that. But for product design and development, there's a lot that AI can do, which people have learned over years and years of study and research. It can combine them and then bring it to you in a form that you leap forward multiple years into that. And what takes maybe a few hundred people to do, you can have AI do the job in terms of the design, in terms of the manufacturing efficiency. You look at the feasibility of doing something and the whole simulation process. When you look at ESDM, you look at, for example, defense, we talk about SWAP. Okay, we talk about size, weight, and power utilization of any component that is being made. So AI can help a lot in doing this optimization and for that particular application, and reading through historical data and saying, okay, this would work for this, it could simulate and then give you a finished product. So I think we cannot stay away from AI, and it's pretty much everywhere. The use cases are pretty much to our own imagination.
So can I ask a question? So I'm actually an artificial intelligence and data science student. So I recently read about NVIDIA's Triton inference server.
Right.
So they were having to see a lot of vulnerabilities which cause code execution problems and all. And it's actually running on the server right now. So there can be problems related to model thefts, or they can install malwares, right? So what's your take on that?
Okay, I am no expert in that topic, but I should tell you, we've got to give everything some evolution time. Okay, so when new technology comes or something new comes in the market, it's bound to have a lot of gaps and loopholes, which over a period of time evolves. Okay, right from I think again I go back to automotive, right? You take a car, maybe the years when it initially came, right? How it was structured and designed, and it had a lot of problems in it, and the reliability has then been increasing phenomenally over time. So this will happen with AI as well, as more and more use cases and people find. But the good thing today is AI helps improve the AI as well. So that's what they are doing, and I'm sure with all these attacks and vulnerabilities that are there, they feed that back into the model and see how do you prevent these attacks coming on.
Thank you, sir.
Thank you. Any further questions?
Good morning, sir.
Yeah.
Sir, what role robotics optimization in manufacturing process?
What role robotics help in manufacturing process? Right. I see robotics helps in any type of an automation where you do repeated work. In fact, I put it where there are something what we call as 4Ds. Okay, is that robotics can do. You typically deploy robotics in 4 things: in dull jobs, dangerous jobs, dirty jobs, and delicate jobs. Okay, these are where you pretty much put robotics in. What can be repeatedly done without much process, you get robotics to do. What is dirty or dangerous for somebody to do, you get robotics to do. What is very delicate, it requires high precision, which the human hands are one of the most dexterous things in the world. But I should say, today if you have to have something that we're talking about in microns and in nanometers, which the human eye cannot see, then you probably robotics can do. So as part of the whole manufacturing setup, where you want to look at volumes and where you can repeat something, I think robotics plays a huge role. I think that's a whole topic by itself, but yes, when you want to look at scale, I think robotics is the one that will take you there.
Sir, my question is, what is the USP of your company against the competitors? Or what are the things you are going to change to be ahead in the industry?
Okay, we are not a design house. Okay, we are not a mass manufacturing company. So a typical USP in terms of a product differentiator does not come to us. Okay, our USPs are slightly different in the range of services and products that we can offer as a one-stop shop to our customers. Okay, so if we go and talk to XYZ company or we address a specific market, if they are able to see that they do not have to talk to 10 other people and they are able to get all services from us, which is related to it. Of course, we cannot do everything. We cannot build buildings and then also provide semiconductor equipment. We are not the same. But when we talk about a solution, if we are able to give an ecosystem of products and services to them, I think that becomes a USP for us. And the other is also in terms of the services that we can offer, right? In terms of the knowledge as well as the post-delivery services that we can offer. These are our USPs. Of course, we would like to ride on the product market that is coming up in India, the manufacturing push that we have, and we are at the moment developing some of our own IoT products as well. So that's something for our next decade that we are looking at. Thank you.
Thank you, sir. It means a lot.
Thank you very much. Thank you all for the opportunity.
Our next speaker, Mr. Pramod Nanjandaswamy, a giant in the field of electronic system design and manufacturing, a seasonal leader with 25 years of experience and currently serving as a Vice President and Global Delivery Head for Automobile and Mobility at Saint Bangalore. He has worked across the countries of US, Germany and Asia in cutting-edge domains such as autonomous vehicles, connected cars and electric mobility. He is also an entrepreneur, venture capitalist and academic council member at JSS University, actively contributing to global forums in technology and leadership. It's a pleasure to have you with us, sir. The stage is yours.
Not changing. Yeah. Good morning, good afternoon, rather than right. Thank you for this opportunity. I think it's by design that Shiv Kumar started because he gave an overview of ESDM, and that forms a stage for my next level of presentation. Right. So it's part of the chaos theory. That's what I believe in. Right. Even though if it happens in the end, you see a meaning to it. So our AI itself understood that it makes sense Shiv presents first before me, right? Yeah. I'll briefly, this is the overall flow. I'll briefly talk about Cyient, the company I represent here, and how does the product development life cycle is changing. Basically what we manufacturing in the end, either it's a silly chip or a product, it all gets into a product which is what a consumer in the end uses. So what is that, some of that is driving this change, and what is the significance of manufacturing itself in a product development life cycle, right? What role it plays and why it is so significant, and what are the innovations that are happening in the manufacturing industry in terms of technology, in terms of trends, and how is it impacting the overall manufacturing landscape. So Cyient, we are Indian MNC, you can call it like that, providing worldwide services, both design as well as manufacturing. That means we do outsource design and outsource manufacturing. When the director sir was talking about medical equipment not being manufactured, at least we are currently designing it in India, right? And some of those parts are also being manufactured, if not all the robotic things. And we do those sub parts, and in the end we export and they get assembled. But there is not, the time is not too far away, because we are already engaged in localization of some of the, what we call as localization means bringing the global products to an Indian market and customizing it as well as manufacturing it locally. So that phase, even for a medical robotic arm, has started. So that way, I think in next 2 to 3 years, you see some of those being manufactured in India as well. And we help in some of that. These are the industries that we work across, whether it's aerospace, automotive, rail, energy, utilities, communication, right? Uh, Engineering the products for all these domains. And we have been in the industry for 34 years now, started as Infotech and then became Cyient. And we have 50 plus strategic customers and worldwide located in 35 technology studios with 22 countries. And this is our global spread. We have around 1,500 engineers in US, another 1,500 in Europe, another 13,000 in India and rest of the APAC. And then within India, we are headquartered in Hyderabad. And in fact, we have very pretty soon we'll open a center in Coimbatore. I already have close to 150 engineers here. Majority of them are power electronics, hardware, and some automotive engineers working for some of our customers out of Coimbatore. We also have, as I said, that what I spoke previously was on the design side. This is on the manufacturing side. We have close to 4 plants in India and 2 in US. So overall 6 plants, manufacturing, aerospace, medical, and some of the consumer electronics products. Idea is to do a low volume but more niche product manufacturing, and that's where some of this thing, defense also is another major area of manufacturing that we play in. And again, all these manufacturing facilities come with electronics, SMT lines, PCB manufacturing, as well as certification lab, EMI, EMC, environmental. So that way it's a full-fledged manufacturing facilities. Now I represent within Cyient automotive and mobility business unit, and we have close to 3,000 engineers working in automotive, and we do work in entire vehicle as a design, if I have to say like that, whether it's mechanical, the body design, or the electronics part of the design, whether it is making the vehicle autonomous or bringing a user experience through a infotainment or a cluster speedometer, or making the vehicle electrical, right? Or manufacturing part of the vehicle or the sub parts of the vehicle. So that way we do end to end, and we are recognized as a world leaders by various industry forums. And now coming to the topic, a product, right? Whatever it is, in the end you can just say that it's a mobile or a car or any of the drones is what we call as product here. And from past at least 3-4 years, that landscape has totally changed. For example, you earlier used to see a model of a car in like 5 to 10 years. Now you see every year some new model coming in, right? That means this time to market, again, probably some of the pressure is mainly coming from China, but it is there for you to see, right? Every year you see a new car model being churned out, and that means time to market, that time has shrunk. And the other one is now today's consumer expect features to be there, every new feature to be available that's already out there in the market, right? No longer you launch a product and wait for 5-10 years and then launch another product. Even if you have launched a product, that needs to be upgraded in terms of features through back-end software upgrade, so that you keep getting new features or app installation, right? Within your mobile, you bring in those apps which uses the data to bring in new features, new UI experience. These kind of things being constant upgradation through software upgrade or dynamic even changing of any of the sub parts, right? You expect it to be upgraded in a way. And product life cycle has shrunk. That is again driven by time to market. Earlier, what we used to think is a 2 to 3 year one infotainment or a cluster or a mobile phone is now like 6 months to a year, right? That means if car has to be launched every year, then our time to produce the sub part within the car has shrunk to 6 to 9 months. That is the level of pressure that we are feeling in the industry, and lot of it is personalized, right? That means you get into a car and you expect it to know who you are. If you are in a good mood, right? You had a good lecture in the class, and you get into the vehicle. You want to listen to the good music. It automatically recognizes your mood and starts playing the song that you want to play. Or it knows you have an exam day and it has to motivate you, right? So it knows today is the exam day and start playing a motivational song that you know from one of your movies, right? So those are what we call as personalized experience. So that is also a demand that is coming in. And of course, everything is becoming software and electronics, right? The mechanical part is underneath is there, but in the end, electronics and software is coming on top so that it becomes a closed loop system. And then everything then becomes self-learning through AI, so that the whole chain becomes more autonomous and self-learning and self-driven also. And that is enabled through data and connectivity, right? Everything becoming digitized and everything becoming connected. And other key thing is also sustainable. You hear this carbon tax, right? Sustainability, green earth, green manufacturing. In the end, everything has to have that green element to it, which is where the sustainability piece is coming to. So these are the things that are more or less changing the entire manufacturing landscape. And where does the manufacturing itself sits in the entire product development life cycle, right? If I am manufacturing a car, for example, I start with the ideation. Ideation is what market I am targeting, what set of people, where do I position this car, how does it, what are the features that it should have, what competition it is coming, it has to address, what could be the price point. Considering all these things, we'll start ideating how this vehicle will look like. And then we make a concept out of it. Concept is, for example, what are the sub parts of it, how do they come together, what sort of architecture, is it like 5 ECUs or 1 ECU, central compute architecture is what we call, or 100 ECU. Then who are the major players, right? That would then become part of this car, major other component, where they will come from. So all this then becomes a concept. And then you start getting into execution. Execution is planning, timeline, cost, budget. All this becomes part of the next phase of making it more concrete requirement, where whatever you have done as a concept start becoming more concrete and start getting into a product development life cycle. So then becomes detailed design and then implementation, verification, and in the end, when the product prototype and all is ready, you hand it over for manufacturing. Ideally, if you look at this whole development life cycle, manufacturing is almost what we call as gate 7, right? So there is a gate 1 to gate 8, G1 to G8, they are called gates. And manufacturing starts after gate 7, where manufacturing, post-production support, and then end of life. So those phases come in. But because of all the things that I spoke previously, manufacturing now starts right in the beginning, right? Because what is the manufacturing cost involved? Is this product manufacturable? Where are the supply chain coming from when I'm choosing a component? Is that component getting to end of line before I even start manufacturing? So, and what is my manufacturing capacity? Should I install more capacity? All this becomes part of the discussion right in the beginning. So that manufacturing then goes hand in hand. How much I should automate? How much is manual? Where do the equipment, if it is robotics or whatever coming in? Do I need to do vertical integration for this product to achieve a better cost? Do I need to do localization? For example, in my previous company, when we did the XUV 700, the twin display cockpit, right? One of the things we were doing was the display system. It's the first time twin display concept as a single display was used in an Indian car by an Indian manufacturer. And from my previous company, we made that whole product. And then the thought process was, where does the display panel come from? How do we assemble it? Where does the back cover comes in? How does the front glass get in a way put into the entire system? Is it liquid crystal adhesive? There are so many technologies that are available. Which technology to use? And it so was happening, we didn't have the technology here in India. So we have to send TFT display from China to Japan, get them assembled there, bring it back to India, assemble rest of the PCBs and back cover, and then deliver it. But later when we brought the technology, we were directly getting the TFT displays from China, do the whole thing here including front glass crystal adhesive, and then started supplying. So that we did it a two-phase approach, right? First phase was just import, assemble. Then second phase was part of it customized to reduce the overall logistic cost. So these are the things that becomes approach of localization. Where do we cut cost? How do we over a period of time improve the profitability of the product? How it is upgradable over a period of time? How your manufacturing has to keep up with that upgradability, whether it is software, electronics, cyber security becomes a major component. That means keys, what we call as security keys, has to be downloaded in the plant. Then plant has to be connected with 4G, 5G because it has to be downloaded from cloud. Majority of the plants are in remote areas. Should we do a base station installation? Whole thing gets into a discussion right in the beginning to enable the whole, because if the product is ready and your manufacturing setup is not ready, you are just losing time. And that's why if you see the product quality, time to market, product cost, change management, sustainability, right, in the end, if you have to sell it to a Europe market, if you have to, there needs to be a sustainable angle to the whole plant. They will look at carbon tax based on the amount of carbon that you have, carbon footprint you are making in making that product. So then accordingly your tax gets calculated. And majority of the customers are now auditing us even for our green this thing, right? What carbon target we have, are we on track to achieve it, what are our plans, how much is it renewable energy, how much is it recycled water. All this becomes part of the customer audit and supplier verification criteria as well. And challenges again is supply chain logistics. We knew semiconductor crisis happened, and then what were the supply chain challenges we had, and then input cost, again automation versus manual, that becomes a key decision criteria. Productivity and efficiency improvement, robotics we spoke about, right? How do we make the constant process more automated to improve the productivity? These are all the things that happens as a discussion when we set up the manufacturing element of a product. What is driving the innovations in manufacturing space? So there are 6 major things that happens in manufacturing, right? Manufacturing is not just the plant part of it. There is a supply chain and logistics angle to it. If a material has to come from somewhere on time or to the warehouse, from where it starts to where it originates. If, for example, US starts fighting over Iran and that route gets blocked, how do you get material from some other route? What are your options? All this, and we have something called within India, right? There is, for example, cities like Bangalore, it doesn't allow you to go between 8 to 8 or 8 to 6, whatever, during peak hours. You can only get the material inside the city during non-peak hours. So all this becomes part of your large supply chain logistics, where there is a free trade agreement, India has a free trade agreement where the taxes are less. So this all becomes part of the manufacturing role play, if I have to say like that, right? Because they in the end do the material negotiation, cost negotiation for the components, taxing, everything becomes part of their responsibility. And quality, of course, is the major thing, right? For example, one of the key things that happened was during the supply chain issues, we took the components were sold in the black market. We had to get from somewhere through some web and then put it into the systems. And we did all the X-ray, audit, everything, but when the actual component got into the vehicle, after a certain period of time, it used to get burnt out. That means the entire product was not usable. It was one of the ICs. Because it is out of black market, you don't know who is selling it, from where you are getting, you just getting it and putting it into the vehicle, right? Even though you had ensured it your all tests and everything. And then that comes with its own cost of quality. You have to recall all those vehicles, replace all the parts, right? That is the quality that manufacturing team has a accountability for. So, and that could become a very huge, just $1 IC can cause millions of dollars of loss, right? So that is the level of quality compliance we are talking about. And data foundation and platforms, because now and more intelligent manufacturing is happening, all the factories are connected to cloud, more from data analytics, what we call as preventive maintenance, right? Because of sensor technology is so advanced, we put sensors in every machine, start monitoring its vibrations, start monitoring the noise that it is making, and over a period of time we can predict whether that machine is going to break or not. So before even that machine breaks, we work towards replacing it so that the downtime is less. And my team, based out of Pune, does this for one of our customers across their locations, and they manufacture biggest machines, construction equipment, agriculture equipment and everything, and across their 20 odd manufacturing plants across the world, 50 members do this day in and day out. They just monitor all their data coming out of all the plants, look at the data, what is happening. Then if any alert is coming in the system that this machine is getting into maintenance, call those plant managers, we alert them that they have to do this, track them that they replace the machine well in advance so that the downtime is not there. So these are the kind of work that is being done from India for global manufacturing plants. And the other, of course, is energy care and sustainability. I already spoke about why it is key, and that's why renewable energy, right, within the plant, having recycling done. So those are the things that you are putting in place. And there is also what we call a supply versus demand. When you are having a high power supply, you put up energy storage places so that you download and store the energy and use it when the energy cost goes up. So because during night, for example, when the demand is low, you may have additional supply of energy available. So you can have the energy downloaded and store it in your local plant and use it during daytime so that the energy cost of overall consumption is low. So those kind of demand versus supply driven energy storage is also being used. Safety is another critical thing. Any plant, if you go, they always have a big number saying incident free days, right? They will quote 400 days, 500 days, because in the end that is a matter of pride, and that is also how they take care of their employees, their safety, right? And that's why that becomes a very key aspect. And that's where majority of the robotic comes into picture, right? Dangerous. Wherever there is a dangerous element to it, you use robotics. Mining is one big example. Now, majority of the self-driven vehicles are done in mining so that where danger exists, you just make those autonomous vehicles run and do the mining, sitting in a cabin here. Asset management, right? All your tracking and even preventive asset maintenance, what I already spoke about, or reuse of asset, all that becomes a key aspect in this entire manufacturing. And now specifically coming to what are the technologies driving manufacturing, and that's where majority of the engineering discipline also plays a role. One key thing is industrial IoT, right? That means IoT has what we call as sensor element to it. The sensor senses and then sends data to the cloud, and then you do analytics and bring it back and do some actuators to use the control the machines. So this whole process of sensor cloud can be looked into. People like electronics, computer science people play a major role here. There is a semiconductor, then a control system, for example, if there are instrumentation people, they also play a major role. Then edge computing, of course, sometimes what happens is you will have cameras installed on the conveyor belt, and if you see some defective part through the camera itself takes an image. If there is a crack or something, you take a decision to remove that defective part from going further, because the more you take it to a next stage, you are unnecessarily adding a lot of components already to a defective part, making the entire product even more defective and losing a lot of money on the way by adding other components. So all this becomes edge computing decision making. That means in that particular phase of manufacturing, decision is taken to remove that element. That means decision is then made then and there itself. That's where again electronics guys, mechanical guys who design these robots, who pull that part out of the conveyor belt, or even computer science guys who write algorithms. So they come together to make this one thing work. Then there is immersive technology, AR, VR, right? That gets used not just in how the whole plant works, like even training. When the new workers come in, entire plant is created like a virtual reality show where you just put on the headset and get into a video game, right? Like that, you get into a plant, he can be trained in a virtual world, taking through the entire plant, so that when he actually gets into a plant, he already knows and gets used. It's like training a pilot through a simulator. So similar methodologies are used even for training people in a AR VR world. And wearables, of course, is another key thing, whether it is helmet, sensing some of the dangerous environmental parameters, if there is a poisonous gas, if there is a high temperature, humidity, all those things are getting monitored either through a wearable or helmet or these kind of things. So that is another. 5G is a connectivity angle. Communications guys, electronics guys play a major role there. And all this is, I told already, where 5G plays a major role is whether you have to download a security key for a cyber security or send the IoT data back to the cloud to do some analytics processing. All that to do cloud computing also, 5G plays a major role in connectivity. And robotics, which we already spoke about, if you see all this, there is overlapping of engineering disciplines. And that's where you guys have to make up your mind. What is your strength? What is your passion? Go depth in that way, but also look at horizontals. When I'm a mechanical engineer, how can I learn some of the electronics and some of the AI part of the right to use, so that in the end I become more self-independent to manage not only my part but things around me, right? Adjoining expertises, areas, so that you grow both horizontally as well as vertically, and both are important to understand the system, product, and create more value, and that's how you can distinguish also. That's why no longer we say mechanical and electronics, we say mechatronics, right? So that is becoming more and more important, and that's how you should start thinking and planning your career as well, and stick to one domain. Wherever we say AI, in the end we say domain plus AI, right? It's not AI stands on its own somewhere. It has to go with the domain, and the domain comes from human people. So in the end, what differentiates you is your domain skill, which AI cannot bring as of now. Tomorrow that may change, but that becomes equally important for you to distinguish and work with AI. So start sticking to one domain and start becoming an expert in that domain, because that takes a long time. Medical guy, I'm an automotive guy. I may understand the language of medical, but I'm not in a position to take decisions in a medical domain because I don't know that domain. Similarly, a medical guy cannot take decisions for an automotive domain. So that's why the domain becomes very important as you grow, right, within over a period of time in your career ladder. Artificial intelligence I spoke about. See, one key thing is just know how I can use AI to make my work more productive, more efficient, and more user experience, right? That's the question when you start asking. You don't have to get into the coding, algorithms and that level, but there are a lot of readily available tools, solutions available. You just know how to use them, right? So how to use AI to make my life more better as a developer or as a person or as an employer. So that's why start thinking in that direction and embrace it than avoid it, right? That's what I can say. So that will take you a long way. In the end, that is whether you like it or not is going to hit you. You better be prepared for it, and then you better make it part of your life than avoid it, because that's the worst thing you can do. So start looking at whether it is through ChatGPT or whether through any other means. What is that you can learn which will help you to bring more value and creativity to your work using AI as a tool or as an enabler. So that is equally important as you grow up or even now, right? And digital twin, this is where the digitization helps. Whether it's making it a virtual VR world that I spoke about, or before we even set up the entire factory, the whole thing first digitized to check the flow, process flow, to check the assembly, right? Whether each of the blocks are kept in a proper order, space constraint, is it minimizing the space and maximizing the turnaround time or manufacturing time, so or reducing the cost. Everything can be virtually simulated, tested, proved, and then only actual implementation can happen. And even when a maintenance happens or when you are trying to move around things, everything can be done in a virtual world before you get into a physical world. That's why the digital twin helps, and this is where majority of our engineers are also working. First in creating a digital twin of the factories, then making sure that digital twin data is used in subsequent use cases for a betterment of manufacturing, either in time, efficiency, and it cannot be done in isolation, right? The world has lot of partners and everything happens through partners, and these are all the companies that we ourselves work with to make this happen, whether it is Microsoft, right, or AWS, Amazon, or Siemens, for example, CAD, CAM, PLM, CATIA, they all come from various suppliers, and IBM. So if you see PTS, System Integration Partner, AR, VR Partner. So there are a lot of companies with whom we partner because they bring the tools, they bring the technology, and where we bring value add is to bring latest of that to our customers and deploy it for the benefit of our customers, right? So that's where the expertise comes in, and that's where we work with constantly with all these companies in making sure we ourselves are upgraded in terms of technology, and we know what to use when and how much of it to use, so that in the end our customers get benefited. If you see MathWorks or DSpace, lot of model-based development is coming into picture, right? So that's where some of those partnership helps. That means you do more traditional way of coding has more or less gone. Now it is all auto-generated code or co-pilot-led coding. So that's where partnership with whether it is Microsoft or MathWorks or DSpace helps in automating testing and some of the simulated areas. For example, if I have to test my car in a snow environment, I don't have to literally drive the vehicle in the snow. I can use DSpace to create the environment, simulated environment, where the videos themselves get simulated in a snowing environment or a rain or a sunshine, and then that becomes an input for my testing. No longer we just drive those cars in those environment and try to test. So similarly, again, everything has a back end, right? Supply chain, PLM, or even enterprise risk, like your inventory management, your costing, all that is where Salesforce or SAP, they play a major role, so that the entire enterprise resource gets integrated into the manufacturing. So yeah, that's all we had as a talk. My fundamental thing is again, learning is constant. Don't think that after 6th or 8th sem, once you have a job, your learning starts. In fact, what you have built till now is just a foundation. The further learning will start building your whatever hall, kitchen, bedroom, right, and then next floor, further floors. Till your last breath, you continue to learn, and that is equally important to stay relevant in the industry and to stay up to date with the skills and technologies, because they are constantly evolving and you have to be up to date with them. And in terms of our own hiring and opportunities, I already mentioned, whether it is mechanical, particularly we work with a lot of aerospace. In fact, we design entire engine, aircraft engine itself for one of our customers. So that way aerospace, mechanical or automobile design, mechanical is a key area that we hire. Electronics is another one, computer science, and then communications. So these are the primary skill set where a lot of hiring happens. We at least take around 200 to 300 engineers, fresh graduates every year. And majority of them how we do is we take them around 7 and do a training, and training itself becomes a project, and at the end of each sem we deploy them as engineers at our end. That's how the process works. So we'll work with your placement officers to take the discussion forward. Wish you all the best for your next.
Thank you, sir.
Any questions? I think Shiv's session closed most of the questions. Yeah, anyway, I'll be there, happy to interact with you. If you have any questions, so feel free to contact me during the breaks or anything. We can always chat. Okay, thank you.
Thank you, sir, for showing us that in this ever-changing manufacturing scene, sustainability and edge computing are distant ideas. Our next speaker is Mr. Rajiv Kumar Srivastava, Senior Director and Site Head at NSP Semiconductors, Bangalore, and a Senior Member of IEEE. A renowned expert in VLSI design and embedded systems, he has led the development of complex SoCs and full-chip architectures. His interests extend into quantum computing, and he also serves as the General Chair for VLSI 2025. As an alumnus of IIT BHU Varanasi, he has made notable contributions to mixed signal SoC and custom IP design. Let us warmly welcome Mr. Rajiv Kumar, sir, to deliver his speech. Sir, the stage is yours.
Can you hear me? I see some chairs vacant here. Those who are sitting back can come here. Otherwise, you won't be able to see the slides. If you want. Okay. Good morning, everybody. I think it's good afternoon. Sorry. Anyway, I think we have two good sessions, and now my session will be more technical, but level will be yours, students. This is more for students. Okay. So enjoy the session. Okay, now I belong to NXP Semiconductors, so I have to present few slides. That's my duty on the company. So you can see we are top 10 semiconductor company globally, and we have more than 11,000 engineers, and most important thing is that we have more than 9,500 patents. That's our main thing. Innovation is our key. We are into automotive, industrial, consumer, and these are our main technologies on which we are working globally and in India also. If you see here in India, we are based in Bangalore, Pune, Hyderabad and Noida. So we have 4 sites, and we have around 4,000 to 5,000 employees working with us. Then this is a very important slide for you. So we have a program, we call it NXP Campus Connect program. So twice a month, one of our experts in one of the field give a lecture online. And what you have to do, you have to just go to the LinkedIn and connect with the NXP Connect, NXP Campus Connect. So please make sure you connect it. And you can see this program is running since 2021, and we have 100 sessions. And these are the topics which we have already covered this year and many more to come. It will continue. So please join that. It will help you. Okay? Then another one is NXP Women in Tech program. So here we select top 75 women in engineering student, mostly in second year and third year. And we have outsourced one agency to give them a professional training for full 1 year. And also we pay around 50,000 as a stipend, not every month, one course. And so that, and also the most important part is that those girls which are selected here, they get privilege when we hire them as an intern. So that is also very important. Then another program is AIM, which we call Artificial Intelligence and Mobility Design Challenge. Here also, this is again for students. We invite students every year to have a simulated model and then an actual, most likely a small car or whatever mobility you want through intelligence. And there we have 3 levels. First is first we just select the team which qualifies to enter this competition. Second is that we have regional finale, so we do for South, we do in Bangalore. So we have students coming from all the colleges across the 4 states joining there. And then we have a grand finale which mostly happens in either Noida or Bangalore. And you can see the prize money. It's not the prize money why we do that. Actually, you learn a lot. You are exposed to our experts. You are given with kits coming from NXP, the hardware kits, and also you get full support from NXP so that you can work with it. Okay, so that's really important. And please, so all these 3 things we are doing, and please try to take benefit of this. Okay. Now let's come to the topic. So if you see here, these are the main domains. I think some of them are already covered. Circuit design, fabrication, silicon validation and testing, packaging, board level design, embedded system, volume manufacturing, and of course, then it goes to the market. I will be focused more on the initial parts, not on the rest of the parts. So let's start with that. Now if you see, this was the first transistor invented in 1947. And now, how many types of transistors we have? You all agree with that? I think you must be studying all those transistors, most of them in your courses also. Now if you see, everything, whatever we are seeing, I think you also said that same thing, it's all possible because of this transistor invention. And that's why knowing transistor is one of the important thing for electronics. Either it's a board manufacturing or even a device manufacturing. So please try to understand, this is very important. I know when a lot of students complain that why we are studying these transistors, but actually everything is depending on that. Okay, so this is very important. Now this is a very famous thing, I think you all know. So I started my career in 1995 as a design engineer, and that time it was 0.5 micron channel length of the transistor. And my senior told that in 5 years this will be saturated and you will lose your job. But I am still waiting for that last year. Okay, we have reached up to 2 nanometer, and you can see how many technology nodes are in production and how fast they have grown. And you know, in the whole industry, this graph combined with the development in software, it's all cycled. If you have a faster transistors, you can have faster software running on the hardware. And that cycle keeps going so fast that the growth has multiplied. And that's why you see so many things happening very fast. It was not earlier the case because it's all chain reaction. Now let's start the chip design concept. Okay, so this is a very simple example. Now what is inside the chip? I'm going a little bit deeper, and I'm trying to connect with your courses also. That's my whole focus. Analog IPs, digital IP, RF, IO interface, memories. Okay, let me explain. Okay, yeah, fine. So these are the main activities which you do when you do the chip design. And chip design is a teamwork, it's not a one-person work, okay? Because we need a lot of different expertise to have that. Now these are the expertise. Let's see. Now let's go to the first one, analog design. We have memories, IOs, standard cells, then we have mixed signal IPs like data converters, and then we have verification also done. Verification means you have to ensure that the circuit will work as a silicon, and that you do through simulations. Now what is desired for that, for you? So first of all, these are the flows. So you have to understand that in design, there are two parts of it. One is understanding of the devices and circuits, and another is the flows through which you run. And you have to learn both. It's not only if you know the circuit design, how to simulate it, how to generate the SPICE netlist, how to analyze the data. There are certain EDA tools. If you are not expert in that EDA tool, your efficiency will go down. So that's very important. So you have to learn both the things. The first part, this part you will learn in your college, and that part mostly you will learn in the industry. And that's how you make a complete designer. Okay? So this is very important. Yeah. Now one more thing I want to show you, that right now you are studying simple gates. Okay, NAND gate, for example, I have taken NAND gates. Now this NAND gate looks very simple. 4 transistors, okay. There is a truth table, fine, what else? But no, that is not the case. When you go to the actual design, okay, you need several forms of the same NAND gate. Now first one is the schematic which you see in your books also. 2 PMOS transistor, 2 NMOS transistors, fantastic. Series and parallel combination. Symbol also you see. But that is not the whole thing. You need a layout. You know all layout? How many of you layout, at least for electronics students, must be knowing it or not? Okay, fine. So layout is the actual pattern which goes to the silicon for fabrication, correct? Anyway, so you need a layout, you need an abstract, you need a very long code for that, although it's very simple, but you need it. You need a behavioral model, you need a SPICE netlist, and you need a timeline diagram. Timeline diagram means how much delay it takes from A to output, B to output, like that. Now what I'm trying to explain here, that I mean we all know big application chips, but try to understand, if you go down, somebody has to do this work also. And that is also very important. This is the, like if you are making a home, you need bricks and iron rods. These are the things. You need that. And that too so exhaustive, and it should be very well designed. And this is one cell. There are 400, 500 cells, different varieties, and for each you need so many views. So that is the importance. Okay? Now, as I covered this analog part, what you should do, this is what I have captured. Good in device physics. I'm only talking of analog, rest of the topic I will cover. Good understanding of CMOS and BJT devices, good in RLC circuits, not interested in software. Okay? Good in signal system, good in Fourier and Laplace transformation, good in feedback and control system. I think most of the topic used. Any response? You don't study? Okay. Now let's go to the chip design and verification. So there are two parts. One is the digital or soft IP. Soft IP is a code which basically describes the functionality of that particular IP. IP, you know, it's a block. It's a small part of chip which represents one type of or one specific functionality. Okay? Functionality you all understand? So we need a functional specification and we have to implement the functionality through RTL code. I'm 100% sure you are all aware of RTL code. Anybody raising hand? Anybody knows Verilog code? Okay, fine. So basically these are the codes which describes the functionality of one particular block. Okay? Say for example, there is a DMA, the memory controller block, which controls the memory operations inside a chip. You know, let's take a simple example of computer. You have a cache memory, you have a main memory, and then you have a hard disk. And if there is a data update in the cache memory, you have to ensure that the same data is updated in all the other memories. So there must be some digital IP which is controlling that. Okay? That's a call and block. And that block can be implemented, the first stage is through a Verilog code. Okay? Which is called RTL, Register Transfer Logic Code. Okay. And then you have to verify it. Verification is also important. You have to ensure what you have coded is rightly written. Otherwise, when it will go to chip, it will fail. So this requires a lot of effort to ensure that your IP will work in the silicon, and for that you have to verify. And there are different methods of verification. Now, for soft IP, so soft IP is more like writing the design into a code form, and it's pure digital, no analog. Okay? And that's why you should, for this, if you want to enter into this field, you should be good in hardware description language like Verilog and BHD, microcontroller architecture, and some protocols like UART, I2C, or common protocols. You don't have to understand everything, but you should have a basic, at least protocol you should understand, so that when you have to learn more protocols, new standards in company, when you go to the company, you can learn it because you know the way. And then verification methodology, RTL simulation and debugging tools, and test-based development. So these are all related to coding, but it's not software. Coding means you have to code your design in a way that it behaves like that. Okay? When you run it, it will behave like as if the block is physically present there. And that is the most important thing. Okay, so this is on digital soft. Then we move to another part which we call hard IP. Hard IP means your same RTL code gets converted into a physical design which eventually goes to the foundry so that it get transferred into the silicon. Okay, and that is also one of the very important phenomena in design. Now here, what you do, first you have the same RTL which you have coded, that gets synthesized. Synthesis means the functionality is back to different gates and flip-flops. All the universal gates, flip-flops, muxes, demuxes, all combines to achieve the same functionality which you have coded in the RTL. Okay? And then next one is do your floor planning. So as I said that, what we see the schematic design, it doesn't go to the silicon. Silicon sees the mask. Mask is coming from the layout, where you draw the geometries of those transistors and connect them. Okay? So it all goes hand in hand. Now, as I think somebody was saying that we have 50 billion transistors. Yeah. Now, you cannot do 50 billion transistor layout by hand. Okay? That's why these processes are adopted, where we start with the RTL code, which is a functionality representation, and there are EDA tools which will convert those codes, simple codes, into a functional gate model, circuit. And that circuit, if you see, that may containing say 100 million transistors. So even your 1000-line code may get converted into 1 million transistors, actual transistors. So that's how it works. Okay, nobody can handle 50 billion transistors in any database. So that's how you go one by one below a step and you achieve to that. So floor planning is basically putting the blocks, because how many of you seen the photograph of a chip? I need one answer. I have asked so many questions. Okay, I will show you. So basically you see, I think in previous slide I show one, maybe I can show this one. Now this is a simple chip at a block level. Block means to understand, to study. This is not the actual picture. Actual picture will be different. But what you see, there are different types of blocks for a specific functionality, and then they are integrated through a common bus. Okay? And then bus will provide all the data transfer between the blocks. And then these are the IOs. IOs means input output device, which will transfer or interface the data input and output from the external world. And these are the IOs which goes as a pin of the IC. You have seen IC, there are pins. So these are the pins. So, and this is one block. Say for example, main memory interface. For that, what we will do, we will write one RTL code which will describe the functionality in terms of coding. When we do the synthesis, it gets converted into a gate. Okay? Gate level netlist. Gate means AND gate, NAND gate, flip-flops, registers. And then we come to the floor planning stage, where we take the layout of corresponding gates and place it here in a way that their connectivity is not very haphazard. I mean the block talking to each other should sit together physically. And that's how we do the floor planning. Once the floor planning is done, we start placing the cells. After that, yeah. So these are different steps to achieve, to place all the blocks physically together, connect together, and also we have a clock tree insertion, because you know all the digital design operate on the clock edge. Okay? So, and all the chip should have a clock, and achieving that clock, that every flop is getting the clock edge at the same time. You have to create a clock tree which is balanced for all the flops. So anyway, let's not go into that detail. You are not supposed to know this. So clock tree insertion, routing means you are connecting all the blocks to each other based on the connectivity of the design. And then you do physical sign out and deliver hard IP to SOC integration. So this was for one IP which I showed in the diagram. And you just repeat the same phenomena for SOC integration also, where you basically combine all those blocks together and repeat the same process. And then you see how your block which you draw has been converted into a real layout. Okay, and this is the layout which will go to the foundry for manufacturing. Okay? Now these are the expertise. So if you are going into this domain as a career, you have to be, there are three main things. One is PNR, place and route, physical design. These are same names. I think you must have heard it by your seniors. Then you have a static timing analysis, which is called STM, experts, and design for testability, which is DFT. I will not go into detail of those technical things, but I am just giving you an idea how it goes. And what you should know, what you should be good at to enter into this particular domain of the design. So of course, one is that EDA tools. So you know Cadence, Synopsys, Siemens, these are the some companies. There are many who basically make a software which basically helps you visually to make the design or to test the design. So you should be good at that. I'm pretty sure some of temp license you must, because these companies also provide a student license. So you must be exposed to that. Then you should be good in Python, or skill is now old, Python is a must. And then some knowledge of foundry rules, because there are foundry rules we have to follow to make sure that our design which is going to the foundry is compatible to their requirements. So those are the some requirements. And of course, elementary idea of the fabrication process which helps in the design. Okay, I think this is earlier covered, but anyway, I will just walk through it fast. So this is the whole process of making. So these, yeah, so this mask. So this mask is the same thing which you saw in the layout. So this is very important that in book you study the transistors. It's very simple to draw the circuit as a schematic. But the actual thing which goes to the layout as a foundry is the layout. And that's why you should learn how the schematic can be drawn into a layout. That is very important. Even you can try for an inverter. That will be sufficient. At least you will learn what exactly, how they are correlated. Schematic is also required because you do the simulations to understand the functionality of the any block which you have made using those transistors. So schematic is required. I'm not saying it's not bad. But once your schematic drawing is frozen after doing all the simulations and it's functionally okay, you have to ultimately make the layout, because layout is the thing which will go to the foundry. And that also requires a lot of efficiency. Okay? Otherwise, the foundry may not have a good yield. Yield means the correct good dies. So these are all the steps. I will not go into detail. Now this is important to understand. So this layout I showed earlier. So this is a top view. If you do the cross section, this is the cross section. If you cut the die and take a photograph from the side view, you can see these are the transistors. And then you go up. These are all metal layers. Today in high-end technologies, we have up to 11 metal layers top for doing the interconnections. Because as we heard, we have 50 billion transistors, the most aggressive chip we have. How you will connect those transistors? You need some metal wires. So that metal wires you can see is basically planar wires here. And there are so many layers, so basically you go from one metal to other, cross it, and then go down to next transistor, like that. So it's connected, okay? So this is very important to understand. And then again I am emphasizing, any circuit has to go into the layout, into the foundry. Please keep this in mind. Okay, chip fabrication process, I think it's the same picture, same source. So these are the some important things to understand. At least you go through it and understand what exactly it means. So this is one important thing, ultra high clean environment. You can see in one of the fab, and for photo I remove the mask, otherwise I have covered till here. Okay, only my eyes were visible. So this is important because you know doping, impurity doping, anybody knows? How to make PN junction? You all know. Okay? Good. At least now I got an answer. So, you know, impurity is so important to define whether it's an N-type semiconductor or P-type semiconductor. And that should be controlled, heavily controlled. Then you fix the doping concentration. That's why cleaning environment is very important. It should not add additional impurity into the silicon which you don't want. Otherwise, the behavior of device will change. So that's why so much cleaning is required. And it's not only trace, but also the whole, I think somebody was saying that foundries are very costly because it has to maintain an environment of 1 ppm particles in the air. That is important to avoid any impurity going to that. Anyway, I will not go into these details, but for foundry, so by the way, I think as already covered, we don't have a foundry up and running today. The very small foundries are there. It's all outside. But I think, Raghav, you remember when we met in one of the AICT meeting, their government of India has launched that all the engineering college should have now a BTech course in technology also. And they are saying, I mean, it's a vision of Government of India that we should prepare not only for our foundries, but for foundries outside India. We should prepare the resources like we did for software or now design also. So that's a good initiative. And I think this is going to grow in India very heavily. And for that, as I said, so this is more, it doesn't have a circuit design by the way. Okay, this is altogether different. And here we need a lot of physics knowledge and chemistry and chemical engineering knowledge. Okay, so, and of course layout correlation of mass with fabrication process, I'm already emphasizing that. Now next is packaging. So you know the wafer, this is the wafer which is used in making printing the circuit to the silicon. And this maximum size today is 12 inch. We have 12 inch wafers. I remember when I was doing my PhD, it was 2 inch wafer only, and that was the biggest one. So you can see that has also grown. And one wafer is processed once. So that means bigger the wafer, more dies you are making in one cycle. Okay, that's why we need bigger wafer. So basically this is small square is one die, one chip, which you see in your different boards. So of course you have to cut it and then you have to package it. Now packaging also is growing in India now, heavily, and I think I will not speak much, but I only want to explain two things. So one, so you have this is silicon and this is the package. So you do the wire bonding, just like soldering, from eye of the chip to the pin of the package. Okay? And the thickness of wire is 21 micron. So you can imagine the fine work done there. Another way of packaging is called flip chip, where you have these IOs are connected to a pump on the chip, and there are circles or pads in the chip package, and you just put it like this. Okay, that is called flip chip. Now why flip chip is costly, but why it is used? Because it has no wire. No wire means no inductor. No inductor means high frequency. You all agree with that? You know, inductor always causes damping in the frequency. RLC circuit, how many of you are in RLC circuits? Any hands? Okay, good. At least I have 4. Good. No, more than that. Thank you. Okay, so this is on packaging. I will not cover that. Silicon validation. Now this is also important activity. And these are all domains. One cannot be all the domains. One will be following in one domain when you grow. Silicon validation is something where you ensure that your silicon is behaving like what you expected. Okay? And there you have to basically check the silicon with the same way you checked in your simulation. And you have to ensure that silicon is behaving like that. I mean, you cannot take a silicon or a chip package die from the company and put it on the board and assume it will start running. No. You have to ensure that it's perfectly fine. And for that, you have to do a lot of checks, actual checks, to ensure it is behaving what it is expected to. Okay? So for example, if we have made a microprocessor, what will be the first thing you will expect from it? That chip. Any idea? First chip it should boot. Okay? If it is not booting, whatever is there is useless. So that is the first step of validation. You have to ensure that chip is coming out and at least responding to you. That's what you call in software hello world. Same thing is applicable to chip also. You have to see whether it's responding to your very first command or not. Then you will go to see whether it's running the Windows or not, running DOS or not, blah, blah, blah. But first thing you have to check whether it's working. So this is all part of silicon validation. Embedded design. You know now, these days we cannot sell a chip without software because of so much digitization. We have a lot of microcontrollers into a very simple system also, because everywhere we need that. And to control that, we need softwares sitting in the hardware. I'm not talking about application software. This is the hardware which is directly controlling this circuit. Okay? And so this is also a big field where a lot of engineers are working. So this can be one of your future career path. Okay? For that, you must have a good knowledge of C or C++. Okay? And this is the place where a computer engineering student or electronics engineering both can go. Okay? And also, you should be aware of architecture of general not all, there are so many types, but at least you know 2-3 microcontrollers and microprocessor architecture. And I'm sure you might be studying in final year. And then understanding of protocols like UART, PCI, or something more if you have in the courses. Okay, final message. This is my last slide. Lunchtime. So, please continue to focus on the course offered by your institution. This is the most important thing. I think you also said the same in one of the answering the question. Don't assume your syllabus is not good. This is incorrect. Your syllabus is very good. Please ensure that you are studying what your professors are asking. Learning basic concepts is a must to enter any domain. I mean, any company will not teach you basics. No one will teach you. Everybody will expect that you know the basics. What they will teach you, which is good for them, not for you. So keep that in mind. And last point, very important. All the CEOs of Indian origin did their graduation from here, in India. Nobody did in US. That's the most important thing you should keep in your mind. Okay? Take any name, whether it's a Google CEO or Microsoft CEO, they are all studied in India only, even in schooling and their graduation. Okay? So please keep that thing in mind, because I have seen a lot of students think that they are not in good college. No, that's wrong. You are in good college. The only thing is that you have to study hard. You have to ensure whatever course were designed by your institute, please follow that and have good marks. Okay, thank you.
Thank you so much, sir, for your insightful words. The students can raise their questions or queries.
Fine.
Sir, can I ask you this?
Yeah, sure.
Okay, so I actually have a friend of mine, he's studying in IIT Kharagpur and he's actually following you in LinkedIn for a long time. So he's currently doing a project on AOIs and he has been discussing with me, because I'm an AI student, he has been discussing of the possibilities of integrating computer vision and deep learning concepts with AOIs. So how do you think the traditional AOIs and the integrated ones would differ? Will it have a long, difference, variation, or how will the efficiency will differ according to you?
Sorry, can you repeat it? I couldn't get the full
sir. I just wanted to know whether how much of an impact can AI make in AOIs? That's it.
In here?
Yeah.
Or in general life?
No, AOIs, the automated optic integration, that PCBs they use now.
Yeah, so see, AI is very good in generative AI. Yeah? Fantastic, everybody's on. But here it's not that successful today. I don't know about future. The reason is that AI requires a lot of compute power, whatever you are using for. And that compute power is so costly that your cost of the product is going high. This is the situation today. We are not in a position to do a chip design. Even coding is not very simple. We do coding, but we have to modify it a lot. So still you have to evolve. A lot of things has to be done. But today we are not in a good, because we are trying that. We are trying several AI tools in our design, but it is consuming so much memory space and so much number of cores to process that and everything is in cloud, so we have to pay huge money to them, and that money is got compensated what we are gaining. In fact, it's much more than that. So it will take time. It may not happen also 100%, but something will happen. Yeah.
Okay, sir. Thank you.
Okay. Thank you.
As we conclude the morning session of ESTM Conclave, I would like to take a moment to reflect on the key takeaways from our discussions. We have explored the latest trends and innovations in the ESTM sector, and we are grateful to our esteemed speakers, Mr. Shivkumar Srinivasan sir, Mr. Pramod Nanjandaswamy sir, and Dr. Rajiv Kumar Srivastava sir, for sharing their insights, experience, and expertise with us today. Thank you, sir.